Hello and welcome. Today we're going to be solving Farmer John's favorite permutation. Given a permutation from 1 to n, a process is going to happen to it that's going to produce a sequence of numbers, and our goal is to go from that special sequence of numbers back to the original permutation. So suppose that P1 through P little n are the numbers remaining. So over the course of this process, elements are going to get removed from the permutation, and let's suppose that these are the ones that are currently remaining. If the first number is bigger than the last number, we're going to write down the second number and remove the first one. On the flip side, if the last number is bigger than the first number, then we're going to write down the second to last number and remove the last number. So suppose our original permutation was this: 7, 8, 2, 10, 5, 1, 6, 4, 3, 9. Then I claim that if we perform this process, we will get the following sequence. So let's see why. So let's write down our permutation here, and we're going to go through this step by step. So we see that the first number, 7, is smaller than the last number, 9. So therefore, we're going to delete the last number and write down the second to last number. Next up, we see that the first number is now bigger than the last number. So that means we're going to delete the first number and write down the second to last number. Then we're going to see that the first number is still bigger than the last number, so we're going to delete the first number and write down the second number. But now it's flipped. Now the first number is smaller than the last number. So what do? Well, we're going to delete the first number, or rather, we're going to delete the last number and write down the second to last number. 2 is still smaller than 4, so we're going to delete 4 and write down 6. 2 is still smaller than 6, so we're going to delete 6 and write down 1. Now, the last number is smaller than the first number, so we're going to delete the first number, write down the second number. 10 bigger than 1, so we're going to delete 10 and write down 5. Now 5 is bigger than 1, so we're going to delete 5, and we're going to write down the second number. And as you can see, we match this sequence. So we can go from the original permutation to the sort of special sequence quite easily. But our job's actually much harder. Our job is we are given this special sequence, and our job is to recover the original permutation. And due to the size of n, right, n can go up to 100,000 in this problem, we're basically guaranteed that we need a greedy algorithm to solve this problem. All right then, so what is our greedy algorithm? We are going to go from right to left over the special sequence of numbers, and we're going to add the numbers to one of two lists. And every time we find the smallest element we haven't seen yet, we're going to switch lists. For example, we're going to start looking for 1. As soon as we find 1, we're going to start looking for 2. And as soon as we find 2, we're going to look for 3, and so on. So every time we see the smallest element we haven't seen yet, we're going to switch lists. So let's perform this on the sequence above. So we're going to start at the second to last element, and we're going to begin by writing down 5, and then we're going to go to the right, or the left rather, and we're going to see 10. 10 isn't 1, so we're going to keep adding it to list 0. And now we've seen the smallest element we haven't seen yet, right? So 1 is the smallest element. We haven't seen it yet. So we're going to switch lists. So we add 1 to list 1, and now we're going to continue on. 6, we're going to add to list 1. 4, we're going to add to list 1. And now we get to 2. 2 is now the smallest element we haven't seen yet, right? It used to be 1, but we saw 1, so now it's 2. So we're going to switch lists again, So now we add 2 here. We add 8 where we added 2. And then finally, we added 3 to list 1. We swap lists because we found 1 and we found 2, so 3 was the smallest element we haven't seen yet. And now there are just 2 numbers that are missing. The numbers that are missing are 7 and 9. They don't appear anywhere in our sequence, so we're just going to add them to our list. So we're going to add 7, but 7's now the smallest element we haven't seen yet, so we switch lists. And then we're going to add 9, but likewise, 9 is the smallest element we haven't seen yet, so we switch lists. So now we have 2 lists, and we need to combine them to get the original permutation. And we have 2 choices. So we can either reverse list 0 and add it to the beginning of list 1, or we can reverse list 1 and add it to the beginning of 0. So if we reverse list 1, we get 9, 4, 6, 1, and then we add to it list 0. And then if we reverse list 0, we get 7, 8, 2, 10, 5, 1, 6, 4, 3, 9. So we'll notice that the answer here is not unique. Both of these permutations produce this sequence. The difference is that this one is lexicographically smaller because 7 is less than 9. So our answer is going to be the smaller one. So to recap, what are we going to do? We're going to start at the second to last element in our desired sequence. We're going to loop from right to left, building up these 2 lists. We're going to then, whichever list has the smaller last number, we're going to reverse that list and then append the second, whatever list remains, to the end. So because list 0 has the smaller last number, we reverse list 0, and then we add list 1 to the end. And this greedy algorithm can be quite challenging to come up with, which is why in these problems it is so important to work through lots of test cases by hand. Sort of the only way you could come up with this sort of algorithm is through sort of working through the test cases. All right, we're now ready to begin going through the code. So as always, our first step is just to read in the input. For this question, there are t test cases per test case. So we're just going to loop over t, and then for each test case, we're going to read in n, the length of the permutation, and then we're going to read in h, the numbers in our special sequence. So the first thing we want to check is if h does not end in a 1, Farmer Nyanj, or however you pronounce that, must have made a mistake. If you go through the test cases, you'll notice that every single test case ends in a 1. So if our permutation doesn't match this format, we know he has done something wrong, and the sequence is not a valid sequence. So we just print -1, and we continue on to the next test case. However, if it does end in a 1, then we'll continue on trying to build up our 2 lists here. So the first thing we're going to do is we are going to create some helpful variables. So first thing is we're going to keep track of all of the elements we've seen so far. This is going to be helpful for determining whether or not we should switch lists. Here I have this implemented as a set just to make the program slightly easier. But if you're not sure how to use sets, you can always switch this to an inverse index instead, and your program will work just as well. Next up, we have min location and cur. So min location stores the smallest element. So this is the one we're currently searching for. So it's going to start at 1. When we find 1, it's going to become the next smallest element we haven't seen. And then when we find that, it's going to become the next smallest element we haven't seen, and so on. Next up, cur. Cur stores which of the 2 lists we are currently adding numbers to. So we start adding it to list 0, then we'll switch to adding it to list 1, and then we'll add it to list 0, then 1, and then 0. So cur is just going to flip-flop back and forth between 0 and 1. Then next up, we have our permutation, and it's been divided into these two lists. So this is just a sort of a dynamic array of dynamic arrays, and we're going to add values to each of these lists, where Kerr tells us which list to add numbers to. So now we're pretty much ready to begin looping over the sequence. So we're going to start at the second to last element in the sequence, and then we're just going to loop to the beginning of the sequence, subtracting 1 each time. I'm just going to call the current element Ellie, and we're going to add this element to element seen. So this just marks off that, okay, I've seen a new number, let me record that for future use. Then the first thing I want to determine is, do I need to switch lists? So I need to switch lists when element is equal to whatever the minimum element or the minimum location is. So if the min is currently 1, then I'm going to switch lists as soon as I find 1. If the min location is 2, I'm going to switch lists as soon as I find 2, and so on. So if I switch lists, I'm just going to update Kerr to be 0 if it's 1, or 1 if it's 0. And then once I've done that, I need to update min location. So I'm just going to find the smallest number I haven't seen yet. So I'm just going to increase min location by 1 until I have found a number that I haven't yet seen. So this line of code always ensures that min location stores the smallest element I haven't seen yet. Next up, I'm just going to add the element to the appropriate list. So I have two lists here. If it's list 0, this will add it to list 0. If Kerr is 0, this will add element to list 0. If Kerr is 1, this will add element to list 1. And this handles all of the elements inside the permutation, or inside the desired sequence. So at this point, we want to pause and make sure we've seen the expected number of elements. If we have not, right, so at the end of going through our special sequence, there should always be exactly 2 missing numbers. If we have not seen n-2 elements, then again, Farmer John's rival has made some sort of mistake, and our sequence is invalid. So we're going to print -1 and continue on. So we just need to determine the number of elements in the set. If it's not equal to n-2, we print -1 and continue to the next test case. However, if we have found exactly n-2 elements, then all that remains is to find the 2 missing elements. And the 2 missing elements are just going to be whatever 2 elements are not in the element seen set. So we can just add to the permutation 1 minus Kerr min location, because that's the first element we haven't seen yet. Then we're going to add min location to element seen, and now we're going to loop over element seen one more time to find the smallest number not in it. So this is going to be the last number, and then we're going to add the last number to the opposite list, right? So when we're dealing with these last 2 numbers, right? So when we did this example, the last 2 numbers were 7 and 9. We add 7 to the list, and then we add 9 to the other list. Great, so now we have a complete permutation, but it's divided into 2 parts. It's divided into list 0, and it's divided into list 1. We have to reverse one of these lists in order to find our minimum permutation. So to do this, we're just going to check which permutation has the smaller last element, reverse the appropriate list, and then print out the 2 permutations appended to each other. All right, we're now ready to submit our code to the grading server, so let's get going here. And we can see that we're going to pass all test cases. So thank you guys so much for watching the videos. I'll see you guys all next season. Bye-bye.